Good morning, Twitch. How's everybody doing today? Throw me a thumbs up if audio's working all right. Oh, it's quiet in Vancouver. I can understand that. Maybe that's not so bad, though. Kind of quiet here in Florida, too. Been raining a lot. Somehow I think that the rain is good, but I don't know. It might not be. All right, let's move over to desktop sharing. This is going to be a meta stream about streaming, which ought to be interesting for a couple reasons. First of all, I paved my machine since the last demo, so all the code is actually being copied over right now. You can see that right here. And second of all, I'm streaming from my new A10 Mini Pro for the first time, which I have to say so far I like a lot. I haven't got everything configured well, but we'll see how it goes. All of the indicators that I have show that it's a really high quality stream. Streaming at 8 megabits per second. So that looks good. All right. So, if you were here for the build stream, the quick and dirty of the demo was that we pretended that I was Matt Damon and stuck on Mars, and we needed a way to communicate. So we replicated the scene in which he used the camera on the Mars rover thing that was sitting there to point at letters, which then translated into hex characters that he used to spell the alphabet, or spell words from the alphabet. And in order to do that, we had to build a secure service using WebAssembly, specifically WASC. And in order to deploy it, we created a WebAssembly service and sent it up to a secure container repository on ACR, and then deployed it using regular Kubernetes tools to Mars, where it then accepted messages and started pointing at things. And that was all managed through a robotic arm that Eric St. Martin built and wired up, and controlled through the WebAssembly using WASC. So let's start from the beginning here and look at WASC. So WASC is securely connecting actors and capability providers. That's its buzzword line here. And WASC I find to be pretty awesome because the idea of hosting WebAssembly on the server is a big deal for me. I think it kind of democratizes the server space. The idea of having the same WebAssembly file hosted on a Raspberry Pi or a big AMD server, it's all the same, and you can do the same thing. What WASC brings to the table there is the idea of having capability providers. So imagine you're building a lot of microservices as a group, as a team, and everybody's creating the same boilerplate code over and over again. We're creating things for logging, we're creating connectors to databases, we're creating connections to Redis. What WASC does is put those capabilities in the host, and then actors that are run, which are basically your services, have signatures that allow them to talk to those capabilities. And the actors don't need to worry about the configuration. They don't care which Redis server they're talking to. They don't care how the logs are written. All they know is that they're logging. And that's pretty nice. I like the whole concept of that. And since WASC compiles down to WebAssembly, and it does RPC-style communication, it's a great fit for Krustlet, which is the project that we're using to deploy this today. So let's go to GitHub and look at Krustlet. So the idea behind Krustlet is that it's an application binary that mimics the kubelet API, talks to Kubernetes and acts as if it's a kubelet. It accepts work from the API server, and when it's submitted with the correct taints and tolerations, that work will trigger WebAssembly workloads to be run by Krustlet. So it removes containers from the equation and allows you to submit WebAssembly workloads in your Kubernetes cluster. So it's really fun, really cool, and it's been a great project for me, especially to really force me to learn a lot of Rust, much learning on Krustlet, and I've enjoyed it quite a bit. So together with Krustlet, we've got a WASC provider that uses the WASC runtime to execute WebAssembly, and then we also have a WASI provider. And the difference between the two of those providers is definitely driven by technology. The WASC provider uses WAPC. Let's see if I can remember the GitHub URL for that. Yeah, WAPC, which is WebAssembly procedure calls. WAPC maps memory spaces from the host and the guest and emulates a RPC call by using memory. That's interesting, especially in the WASM and Kubernetes model, because WASI as a specification right now does not support really any host networking. So you can't start a web service as a WASI executable. You can consume things on files because you can map files in from the host to the guest, but there really is no networking protocol. So WASC is a great way to get around that networking issue and provide a network type service on a WebAssembly runtime. WASC has an HTTP provider, so we can do an HTTP endpoint. And recently they even added a telnet provider, which is crazy. And now there's a telnet endpoint for WASC. So we started with the idea that we needed to communicate to Mars. And we knew we had a Kubernetes cluster, a fake Kubernetes cluster up there, and we needed to be able to create this secure capability that would talk to our robot. So in order to do that, let me open up WSL. Let's hope that all of my files for that particular project have finished syncing. All right, so a moment ago when I was talking about capabilities providers, in WASC, there are known capability providers and there are custom capability providers. So the known capability providers are things like HTTP server or logging or Redis, but you can also create your own custom capability providers. And that's what I did in the case of this demo for last week. I created a where's our crates here? I created a WASC robot capability and added that WASC robot to the Krustlet host. So let's go backwards from that concept and talk about how I created a robot capability provider and then added it to the host runtime so that any running WebAssembly module could call that robot capability if it were so authorized. So this code, the capability provider code here is all pretty straightforward. It handles messages that are sent by the host runtime, sent by the guest, the actor, into the capability. And the capability provider then just checks the type of the call and handles it appropriately. So the first thing that happens when you register a capability in the WASC runtime is it has to configure itself. And that can be dramatically different depending on the capability. So you might have a capability that needs state for connections. So if you've got a Redis capability provider, you're going to create a connection to Redis, and that's pretty straightforward, but you need to maintain that state throughout the runtime, and all of the clients will use that same connection over and over. In our case, we're actually using a serial connection from the host, and that serial connection opens up dev TTY USB 0, which is the port that the USB plug was plugged into for the little robot arm that we were using. And then we do some Rust to open up that serial port and make sure that it's available. And if it is, then we do this crazy lookup table, which is porting these hex letters, hex codes, to robot arm positions. The arm had 6 degrees of freedom, so each one of these positions represents a target for that particular rotor to show where the arm points on each of the axes that it can move. So if you remember the Mars thing, there was a circle with letters at varying angles of the circle, and this first axis, I couldn't tell you what the first axis might be. The hand, the gripping hand, doesn't move at all. The second axis doesn't move at all. But then you notice that these other axes start to change as the arm rotates around the circle to show where the arm is pointing to. So we have this lookup table that shows where the letters are, and then some simple code that sends the phrase to uppercase and then collects the letters and starts to iterate over touching the letters. So if you send me A, we're going to translate that into hex and then touch the letter for the 2 hex codes that represent the letter A in ASCII. And all of that happens once per call from the host. So we've got our robot code, and we need to take that code and register it in the WASC provider. So our binary that we run is Krustlet WASC, and this is really just the simple main code here that instantiates a WASC provider. The WASC provider itself is here, and in the WASC provider, there's a bit here in the module store where we have to instantiate each of the capabilities that we're going to allow to run on this host. So again, Krustlet isn't necessarily a generic provider. It's just an example of how you can create a provider, especially when it comes to things like custom capabilities. You might want to have very unique capabilities that are compiled into your binary, and you configure them per host. So it might not necessarily be something that's just cookie cutter and you can create them and ship them everywhere. You might want to have a different WASC provider binary for very different situations. In our case, we've got this robot provider. So we're going to instantiate the robot provider code and allow it to be a native capability that is then called from actors. And because that code is so unique, that's why I say it would be kind of useless to have that built into a generic binary. Oh, Kevin's joining us. He's the primary author of WASC, and he says capabilities can be loaded as runtime plugins, compiled into the host, or even into other WASM files. And that's a very important point. In this case, I compiled it into the host. rather than loading it from a dynamic library. The other option here would be to read a dynamic library off of the disk. So pre-compile that robot, read it off of disk, and then load it in. But I chose not to do that. I chose to compile it in directly, mostly so that the compiler and static typing would be my friend while I was building the demo. And I suppose I should make this bigger because I forgot I'm streaming at such higher resolution here. All right, so that's the first thing that we do. We instantiate these native capabilities and allow our provider to be called from the host itself. And then down at the bottom here, when the runtime starts, it will eventually call WASC run. So after we've submitted a Kubernetes workload, we're going to call WASC run. And here we have to do some of the setup for our capability provider. So we've got an environment that we're going to pass to the robot, and it's basically empty. There are no configuration values, so you can see it's all empty. And then we push the capability into the actor. So we tell the actor that it has this capability, and then we execute the workload and try to configure that capability for a particular WASM module. And that brings us down to the actual demo code here. So the Mars demo code, this is the actor that gets compiled to WebAssembly, and it's the thing that actually does the service. This is what you would think of as the microservice. So we've got a method that handles an HTTP request, and first thing it does is check the query string on that HTTP request and look for the call that we're going to be making to our robot. So you pass in $Brian, it's going to send Brian. And now the actor, which is this WebAssembly module, has the ability to call functions on the host. Our function is an untyped function. It's an anonymous, unnamed provider, because we didn't go through the extra ceremony of creating types for the provider name. So in this case, our untyped provider is called default, and we're going to call the WASC robot transmit message RPC call with the query string as the parameters to that. So as the guest, as the actor here, when we receive a network call, we're going to ask the host to operate the transmit message function for the WASC robot capability provider. And that WASC robot capability provider transmit message function will get handled here in the capability provider for WASC robot, and in transmit, op transmit, it will send the body to the robot code that Eric wrote, and the robot will do its movements, which will be really cute, and then we'll send back an OK. So that was the Rust side of this code, the kubelet and the server side of the code. In order to build this, I always lean on makefiles because there are just so many steps, especially in this WASC and WASM world, because we've got to compile our code as WebAssembly. So there's this special Rust incantation to do that. And after it's built, we have to sign it using the WASCAP tool, which is a secure signature, a digital cryptographic signature that tells the host who owns this actor and what things the actor is allowed to do. So we're signing it with the capability of WASC robot, which means that it will be allowed to call the WASC robot transmit message function. So we've got all these signatures, and then the last thing we need to do after it's built and signed is we need to push it to an OCI registry. And for that we use GitHub, WASM to OCI here. So this is a hack isn't quite the right word, but it's a fun tool that uses the unique properties of an OCI registry to set MIME types for artifacts that are WebAssembly. So if you look at the OCI artifacts proposal, which is linked in here, it talks about how to deploy artifacts using MIME types, and this project creates a couple MIME types specifically for WebAssembly. So there's vnd.wasm.config and vnd.wasm.content.layer. So we're sending WebAssembly up to a container registry as straight bytes instead of as Docker layers, which is what OCI registries were built to create or to store. And that's kind of fun because we can store these WebAssembly files in a secure way in registries, and it works with the Kubernetes tooling that we're already used to. So in the Kubernetes deployment manifest for our Mars actor, after it's been sent up to the Azure Container Registry, we have a deployment manifest that mentions that container, that image file, at webassembly.azure.cr.io mars-wasc version 0.5. It took me 5 times to get that deployed into a container registry image that worked. Don't laugh. We tell it it's going to listen on port 8080. And the most important parts of this particular deployment manifest are the tolerations and node selector. So we're telling it that it needs to run on a node that has WASM32 WASC, and it has WASM32 WASC tolerations. So when our kubelet starts, it will declare that it has this capability for architecture, and that it tolerates the WASM32 WASC no execute toleration, and that will allow it to get WebAssembly scheduled. And that's really fun to watch when the WebAssembly kicks off. So after it gets pushed up to ACI, it gets pulled down by the kubelet, and the kubelet starts a pod that happens in the WASC provider here. Let's find that code down here. So we've got the host. This is the WASC host. We're going to add the actor, and the load is the actual WASM file for the actor. So the WASC runtime adds that WebAssembly file as an actor, configures the capabilities, and then returns OK after it's spawned a handling task for the WASC runtime. And at that point, the execution of all of the WebAssembly bits are in the WASC host runtime's hands. So that WebAssembly call, the HTTP call, will get managed through the WASC host runtime and then sent back up to our provider through Krustlet and then back across the network. So I started the kubelet on an Intel NUC sitting on the floor in front of my desk over here. And the NUC had the robot plugged into it by a USB port, and it was in my private network here. So how did we make that part of the Kubernetes cluster that we could talk to from the internet? It's a great question. I did that with 2 pieces. First is Tailscale. So with Tailscale, I have the ability to create, just go to tailscale.com, to to create a VPN network, and it's private using WireGuard in the background. And Tailscale is just all kinds of awesome. So if we look into my dashboard, I think I need to use a different profile. There we go. So if we look at my dashboard, we can see my admin console, and it shows all of the machines in my network. So these are the different machines that I have registered with Tailscale. So we've got my laptop, my iPad, my NAS, my big desktop machine, and this particular one, which is an Azure virtual machine. So we're going to go to that virtual machine now and take a look. Oh, that's not it. I wanted this. So you notice I'm using the Tailscale IP address to SSH to that machine. And that's because the SSH port is not open to the public. So the only reason I'm able to SSH to this machine is because I have Tailscale running. So I've got my WireGuard VPN protecting this node from nefarious SSH traffic, and that's fun. The ports that are open are port 443, and that's running Caddy. So if we go to etc Caddy and look at the Caddy file, I'm still running the older Caddy 1. I've got a entry here for rover.brian.dev, and it's running through WireGuard, proxying to port 18080, so 18,080 on the NUC sitting in front of me. So it's using WireGuard to reverse proxy traffic from the internet at rover.brian.dev directly to the NUC inside my LAN. Now, this won't work anymore because the LAN's actually not even plugged in, but that's how it worked during the demo. So I used Tailscale to pipe that traffic from the internet into the NUC, and that's really nice because I used Caddy to create the TLS certificates for us using Let's Encrypt, and I didn't have to worry about exposing my home network to the internet directly. I have this buffer with TLS out on the Azure VM that I have running here. So I kind of like that. That worked out really well. And then the last step involved the Azure static web app. So let's open that. See if I can find it, because I don't remember where I put it. There's nothing in there yet. I don't actually remember where that project is. I'm going to go look on my laptop real quick and see if I can look at recently opened bits. Help me remember where that project lives. Oh, it's in temp. All right, let's see if temp is synced yet. No. So temp is still syncing over here. But it's on GitHub, so let's go up there. So this was the front end to the site. And the front end to the site is a simple, svelte JavaScript application that accepts messages that you display on the screen. So you type into a form, and it publishes those messages to the endpoint of my Azure VM, which then tunnels them back to to the house and runs them on the NUC. But I knew that this was a demo for Microsoft Build, and I was incredibly nervous about opening the demo up for people to submit code or submit words that could potentially be less than friendly. So I had the inspiration to use Azure content moderation services, and I used an Azure function to accept the message and then submit it to Azure Content Moderator. And in the Azure Content Moderator, if it found anything that was considered risque or offensive, Azure Content Moderator would just fail. So if it failed the message, we'd send back the status of fail and then the length of the terms, if there were one or more terms in the message that failed the Azure Content Moderator. If it didn't fail, we would submit it to that rover endpoint with the message as part of the query string, and it would submit that out to the robot. And that worked out really nicely. We were initially really nervous about opening that up for the world to publish messages, but adding that content moderation made it a lot nicer. And at the end of the demo, it was a lot of fun to just sit and watch the messages come streaming through, showing that it worked across the internet and that people were able to submit these messages directly to the robot in the house. That was a lot of fun. So the source code for that app is really tiny. It's a Svelte app, and if you haven't noticed, Svelte is pretty much the only way I want to do JavaScript anymore, which is kind of funny. This app has a form with a message that's bound to the form field, the input field, and then a little bit of state management for the button, so that if the button gets disabled after you've submitted it, and we wait for the content moderation to work. And then I added a typewriter effect up here at the top, so that if the message came through, we would make it look like there was a typewriter typing on the screen, and that was really fun for the display effect. So it would say sending message, and then it would show the hex that was getting sent, and that was really slick. So then, after the state management bits, all of this was set up to deploy to Azure Static Web Apps. And Azure Static Web Apps are a new feature that we just recently added last week. So let's see if this still works. I'm going to switch to there we go. Don't need to be seeing my sign-ins here. All right, so Azure Static Web Apps are the way that we can deploy Jamstack type applications in Azure. So let's type in static. There we go. And we can go ahead and just deploy this app to show what it looks like. So we have to give it a subscription and a resource group. Then we'll give it a name. And then a region that we want to deploy to. Go ahead and sign in with GitHub, and it'll ask me what organization. And then it gets a list of my repositories. And we'll deploy master. So now it wants to know where the app is in relation to the repository itself. And we just saw that the app lives in public after it's built, because it's a Svelte app. So we're going to /public here, and tags, and create. And what this does is connects the repository to Azure Static Web Apps with a GitHub action. And let's hit create here. And then we can modify that action to make sure that it's actually building our web app correctly. So the resource is complete, but it hasn't yet been built. And we've got a URL of Icy Island with some stuff at azurestaticapps.net. So if we open that up, we should just see a message that's telling us that we're ready to rock, but there's no content yet. So let's go back to GitHub and look at the actions. So you can see that we have a new trigger that was triggered by the Azure portal when it added our static app workflow file. And what it's going to do is build and deploy our app. But the real question is, what does it think it's going to do to be causing that build? So it's going to check out our repository, and it will not actually do any building. So, I mean, in theory, this shouldn't work unless that build and deploy web app thing is smart enough to know about our Svelte app, and it might be. So let's see how our GitHub action goes. Yeah, it failed. Not surprising, because there's no actual building going on. Failed to produce artifact folder public. So we need to tell it how to build our app. So if we go back to GitHub action, oops. I'm going to cheat and look at commit history here. This is the file that we deleted previously. And you can see that oh wait, was I as foolish as just screwing up a slash? It was. Alright, so let's go ahead and edit that in place. Get rid of the slash for public. That might actually build. If you have something complex for Azure Static Web Apps, you can completely modify the deployment script. And I'll show you an example of that, because I'm doing some crazy stuff over here. Decided to put all of my content in this big mono repo, and for the deploy, I've got crazy things happening. You can CD into the GitHub workspace and do an npm install, start running node processes. So this one is creating short codes to my URL shortener. It's submitting talks and building slides, and and then running yarn and yarn export for the Svelte site, and then deploying it to Cloudflare. So you can do all kinds of crazy things in these GitHub actions, and you're not limited to the simple build workflow of Azure Static Web Apps. All right, so now that I fixed that slash, it built the directory and it's uploading it to Azure Static Web Apps. And then it just polls waiting to see when that application is done being deployed. And it's done, so we can go to the URL and see our app, and it's going to submit it to the content moderator, and it's going to fail because it isn't able to submit it into our Kubernetes repository, which isn't unexpected, but it is fun. And it's probably important to note here that this static web app has an API directory, which is for Azure Functions. So all of the serverless bits of this automatically get deployed when we do the static web app build here in the workflow file. So that's really neat. The Azure Functions just automatically get deployed with the app, and both of them work at the same time. So let's look at the console here and show that it failed to post because the server responded with 500, and that's not unexpected. Oh, actually the server responded with 500 because I didn't set the API keys for content moderator, which is good, because if I had checked them in to GitHub, that would have been a sad state of affairs. So that's pretty much the end-to-end workflow. I went through it backwards because I think it makes more sense that way to talk about what our end goal was, moving the robot arm, and then work back to how we were going to communicate with it. But I had a ton of fun building it. It really was a great demo project to show all of the things that you can do with WebAssembly and Rust and WASC capabilities really shined here because it allowed us to create a custom capability that was on the host, and the actor was able to call it without having to stress about how we were going to communicate with a serial port through WebAssembly. So that was particularly neat. Behind the scenes, we had actually just finished compiling the WebAssembly runtime Krustlet on a Raspberry Pi literally half an hour before the demo, and Eric St. Martin and I looked at each other and thought, should we try to move this demo over to a Raspberry Pi, thinking that it would have a lot bigger effect if it was running on a Raspberry Pi. We decided that that was just too much risk, but definitely in the future we will run this same demo on a Raspberry Pi running the Krustlet instead of on an Intel NUC, because I do think that that would have a bigger impact, and it shows the promise of WebAssembly, I think, better running it on an ARM device that's joined to a Kubernetes cluster that doesn't necessarily have all Intel machines. So that's pretty much it for my behind the stream demo. If anybody has any questions, now's a great time to hit them up. The source for the web app is at bkettleson, SWACOG, which is Static Web Apps Cognitive Services. That's what that stood for when I was naming it. And the website for WASC is WASC.org. waSCC.dev. There is a Zoom meeting every Friday at 1 p.m. Eastern that I host for the WASC runtime, and we've had some fun conversations with people from all over the world talking about how they're using WASC for what I honestly think are crazy things, just really cool projects that people are using WASC for. So you can go there, and then the Krustlet Krustlet repo is at GitHub, and that's Deus Labs. And Krustlet has a Monday meeting. I'm not sure. Yeah, there we go. Weekly Zoom call at 9 a.m. Pacific every Monday. So if you want to get more information about Krustlet, running your WebAssembly workflows in Kubernetes, Krustlet is pretty awesome, and I see a lot of exciting potential in Krustlet, enough that I've dedicated much of the last 4 months to work on Krustlet specifically and learn Rust, just so I could contribute to this project. I think it has enormous potential. So thanks for tuning in and listening to the behind the stream story. It was the most fun stream I've done ever, and certainly one of the most fun projects I've ever built. Very grateful to everybody in the Deus Labs team for their help putting it together, and especially Eric St. Martin for making the robot bits work. And he and I came up with the idea to do that Mars rover thing, and he talked me into using the robot arm. I was just going to do a little motor that rotated around like a clock, but Eric talked me into going crazy. And it seems like when Eric and I do projects, it always goes over the top, and it's always fun. So that was fun, and I appreciate everybody watching today. So follow me on Twitter at bkettleson, on Twitch at bkettleson, YouTube bkettleson, GitHub bkettleson. That's it. Have a good day. Thanks, everybody.